This is 1.3 day 4. I'm Mr. Bishop, and we are talking about linear functions. This is actually the continued version. We're talking about linear functions in the last notes for day 3. We're going to continue talking about linear functions in these notes. So let's start with the idea of graphing linear functions. If you think about the horizontal axis, the one that runs right-left, where the graph hits that axis, we can call that the x-intercept. So I'm going to make a really crude graph. It's not even going to be linear, just to give you an idea. If we just make any old graph here, let's say there's my axes, there's my graph. Again, it's just a rough sketch, not even linear. But you know where it crosses the x-axis, that would be the x-intercept. So a couple important features about that. The y value at this point has to be, well, the height is 0, right? So no matter what this x value is, I'm not sure what it is, the y value has to be 0. So we can say for the x-intercept, it's always going to be x comma 0. Whatever x is, I'm not sure. But I can kind of show it visually here, my rough sketch. I'm actually going to go ahead and erase this guy, now that we've got the visualization in our mind. So, how do you solve for this value x? If I gave you the equation, if I gave you the formula, it's actually really simple. You substitute 0 in for the y, and you solve. So I know we're used to dealing with y-intercepts a lot, but it's also worthwhile to think about what would happen at the x-axis, the x-intercepts. So we don't know what the x value is just by looking at the graph necessarily, but we know the y value has to be 0. But if I gave you the formula or the equation for the function, if I asked you what the x-intercept was, all you'd have to do is throw 0 in for y and then solve for x. Okay, so enough about the x-intercept. Let's talk about that vertical axis, aka the y-axis. So where the graph hits the y-axis, that would be the y-intercept. So I can make a really rough sketch here again. It's not even linear, but it shouldn't really matter for this point. Wherever the graph hits this vertical axis, that would be the y-intercept. So you should kind of notice a pattern now. What would the x value of that coordinate be? Well, right, left, it looks like it'd be 0. So for the y-intercept, it takes place at 0, comma, y. Whatever that height is would be the y value. If you're someone that notices patterns really well, you probably know what I'm going to say about solving for the y-intercept. Right? You kind of just flip the script here. Plug a 0 in for the x, right? Substitute 0 for the x, because we know the x has to be 0, and then solve. Solve for y. So kind of a flip-flop pattern there between being able to solve for the x-intercept and being able to solve for the y-intercept. Maybe something you hadn't thought about before, or if you had, maybe you're just refreshed on it. Okay, let's look at the first example here, example 1. I'm going to start with just p and q being two different functions. I could use f and g. I can use really any letters, right? P and q are going to be two functions. And we're going to look at them together on a table. So it's important that we are familiar with the inputs and outputs that go into a table so we can read those and tell what's going on. So on the top, p and q are the functions. Those are the outputs. Remember the inputs, we can use x. So x will be in the first row, right? We're going to run this one landscape side to side. And then the outputs for p of x can go here. And then the outputs for q of x can go here. So could I have made two separate tables for p of x and q of x? Yeah, sure I could have. But this is way more convenient, and now I can stack them up. So for both of these functions, the inputs for x are going to be the same. So let's go ahead and get those now. We got 50, 55, 60, 65, and 70. Remember, x is the independent variable. It can do whatever it wants. And then how do you get these values? Well, you would plug it into the function and get your output. So in this case, they're actually going to be different for p of x and q of x. They're two different functions. Now, I didn't give you a formula or a graph for either p of x or q of x, but I am giving you tables and basically points, so values along that function. So here are the values for p of x. 0.1, 0.11, 0.12, 0.13, 0.14. So if we just focus on x, p of x, like for example, this point, the input would be 50, the output would be 0.1, right? That would be a coordinate point on the graph for P of x. Okay, and let's go ahead and get the values for the Q of x. So we know the inputs for x. What would the outputs be for this Q of x? I'll go ahead and give those to you. 0.01, 0.03, 0.06, 0.14, and 0.15. So again, let me remind you, there's a couple different ways I could organize this table. This one seems to be the most efficient as far as space goes and being able to stack these up though. I could have made two separate ones for like x inputs, P of x outputs, that function, and I could have made another one for x inputs, Q of x outputs. But for comparison, we're going to use the same x inputs for both functions. Now, they could be two totally different equations. In fact, they would be, because they give totally different outputs. So when we start to look at these and compare these, the first part I want to ask you, part A, could either P or Q be approximately linear? So just based on this information alone, you've got the table of inputs and outputs for the P function and the Q function. What do you think? Could either P or Q, or maybe both, be approximately linear? So if we just inspect what's going on here in this table, the x's, those are staying pretty constant, right? They just go up by 5 every time. So if it was a linear function, the outputs, whether it's P or Q, the outputs should be going up at a constant rate too. Since the x's are going up at a constant rate, we should see the outputs also going up at some constant rate. And I think you notice that with P here. So P goes up by 0.01, and then another 0.01, and then another 0.01, and then another 0.01. So if we can observe that between these points, it stays constant for the x and constant for P of x. Right away we know that that demonstrates a linear pattern. So P, we didn't even have to calculate any slope formulas. We can just observe. It's linear because it's got a constant rate of change between all points. Graphically, you would say it goes up 0.01 over 5. Up 0.01 over 5. Rise over run. Now, could you have actually calculated the slope between each pair of points like we did in the last notes? Yeah, you could have. But I think we can kind of see ahead in this case that this one goes up constantly on the x's, and the P of x at the same time is going up at a constant rate. So right away we know that's a linear trend. Great. So P of x, linear function. What about Q? So the x inputs are the same. Now we have the Q outputs down here. So the x's are going up at a constant rate. Again, we know those go up by 5 each time. But are the values for Q of x, the outputs here for Q, are they going up at a constant rate? They're definitely not, right? This one goes up 0.02, and then from here to here, 0.03. Oh man, bigger jump, small jump. So those are all varying. Those are all different. So right away we can say, whoa, that's not a constant rate of change. Q is definitely showing a nonlinear pattern. Because while the x is increasing at a constant rate, which is nice, Q of x, the output values, increases at varying rates. It's not the same each time, right? Varying means changing. Some of them are bigger, some of them are smaller. They certainly weren't constant. So we know for sure Q is nonlinear. Part B, I don't have any room here, so I'm going to go get a fresh page. I'm going to go ahead and copy and paste. This will be example 1 continued. I'm going to go ahead and copy and paste that same table up here so I can use it. You obviously wouldn't have to rewrite that in your notes. Part B, that you do need to write down, could you write an equation for P of x? The reason I don't ask you about Q of x, because we really don't have any idea, right? It's bouncing all over the place. We need to get our calculators out and do some sort of regression, if you remember that. We're not going to worry about any of that right now. We're worried about linear functions, and we said P of x was linear. So could you go ahead and write me an equation for that line? Okay, one thing we know we need for a linear equation is the slope, right? The rate of change. So the slope in this case, using this notation, the change in the P over the change in the x, right? Remember before we just said change in the y, but now we're using function notation. So what is the change that happens among the p's? And if you look at it, you move along here consecutive terms, you can kind of see it, right? That's 0.01 every time on the p's, the outputs here. And the x's, we see the change in the x's every time is just 5. If you're not comfortable with that, go ahead and grab 2 points, use the slope formula, right? You'll get to the same place. 0.01 divided by 5 gives us 0.002. That's our slope for this linear equation for p of x. Awesome. We got our slope. We looked at the change in the outputs over the change in the inputs, got our slope. Great. Now what do we do? So there's still a couple other components that a linear equation would have. You need to either use a point, or you need to know maybe what the y-intercept is. I like to use something called point slope form. You should remember it now that you see it, if you don't already. Y minus y1 equals m times x minus x1. That's point slope form. It's the most convenient one as opposed to using slope intercept form, which is y equals mx plus b. This one's actually going to turn out to be way more convenient in this case. So we got the slope m, that's done. The x and the y here, those are going to stay as variables, right? We need a y and an x in our actual equation. But the x1, y1, the ones that have numbers as subscripts, those are ones we're going to replace with actual values. So the x1, y1, you just need to pick a point. Any of the points from p of x. Pick your favorite one. I like to pick typically the easiest one and plug it in for the x and y here. So how about the first one here? 50 comma 0.1. So 50 comma 0.1, 50 goes in for the x, 0.1 goes in for the y. And remember, I'm talking about the ones with the subscripts. So let's go ahead and do that. Y minus 0.1 equals 0.002, and then parentheses x minus 50. Okay, this is really excellent right now. Technically, this is a linear equation, right? So the equation component, like I could put a check mark, like yes, equation, done. Although it did say something about p of x, and ours doesn't say anything about p of x right now. So you would need to go ahead and put this in function notation. And for me, I would go ahead and simplify this. Let's just get y by itself and then throw it in function notation. So to do that, we got to distribute this 0.002 through, and then we got to add that 0.1 over. So let's go ahead and get y by itself. Distribute that 0.002 piece through. That should be 0.002x minus 0.1 now. Oh, that's going to be nice. Look at that. When you add that 0.1 over, we just get y equals 0.002x. And now this would be in slope-intercept form. You got the slope. Oh, there's no intercept, meaning the intercept should be 0, right? Okay, why did I go through that trouble? Because now it's really clear. If I want to put this in function notation, it asks for something about p of x. Mine doesn't say anything about p of x right now. But you know you can replace that function notation piece where the y is, right? That's our output. So let's just replace that y with p of x, and we'll be all good. There's our final answer. There's full credit. We got the equation done, check. We got the p of x function notation part done, check. Okay, I'm actually going to erase those. Don't want to scuff up my notes here. Cool, so far we said just by looking at the table and the trend, we noticed p of x was linear, and we're actually able to write an equation for it. Part C, the last component for this problem. What are the coordinates of the x or the y-intercepts? Well, I kind of already mentioned it here a little bit ago. If you're looking at this function right here, the way it's written, you could probably identify that the y-intercept is 0. What's the x-intercept? Well, let's start with the x-intercept. So remember, to find the x-intercept, you plug a 0 in for the y. So in this case, you could plug a 0 in for p of x, and you solve for x. So if you do that, you get 0 equals 0.002x. You divide by 0.0, well, look, it goes through 0, 0. Right? And if the x-intercept is 0, 0, doesn't that also mean that the y-intercept has to be 0, 0 as well? If you don't believe it, solve for the y-intercept. Plug a 0 in for x, 0.002 times 0, that's gone away. we get y equals 0. So that one's 0, 0 as well. Fancy way to say this thing goes directly through the origin. All right, great. Let's go to example 2, and this is our last example for these notes. I'm going to put you in a little scenario here. Mathnasium. It's a place that tutors students, presumably on math. Okay. We're going to talk about their profit and cost. They rent an office for, say, $1,600 per month. I don't know these numbers to be totally true, but we're going to use them for our example. So they pay $1,600 a month rent for their office. Great deal. Tutoring 8 students in a month earns Mathnasium $440. Wow, good for them. So part A, I want you to write the linear equation for the monthly profit. Write the linear equation for the monthly profit. Okay, well, the $1,600 per month rent, that certainly isn't profit, right? They got to pay that out of their account. They're losing that money. But apparently, they tutor 8 students, they're making profit. So $1,600 a month is the flat fee that they get charged for rent. In terms of our function in the graph, that's going to represent our Y-intercept. And make sure, look at that, it's negative $1,600. All right, that's money that they are losing. Now the question is, how do we come up with the slope? Well, we sort of have this rate of change thing going on. It looks like 8 students, $440. So if we can think about that in terms of 440 over 8. So the money you make over the number of students you tutor. If we simplify that down, money over students, we get 55, and let's be careful with the units here. We got money on top, students on bottom. So we're looking at $55 a student, what they get in profit. We'll assume it's fixed. They all get 1-hour sessions to make this thing easy. So that's our slope, $55 a student. So if we could go ahead and write the line, we got y equals 55x minus 1,600. But in terms of their profit, let's go ahead and give it some function notation. P of s equals 55s minus 1,600. So s, you can probably guess, that's the number of students they tutor in a month. P of s will be the profit. Right? We often use capital P to represent the profit function. You could probably take a wild guess to guess which letter we would use to represent the cost function. I'll leave that one to you. All right, part B. Interpret the slope and the y-intercept of this line, which means explain it in words. What the heck's going on with those values? So let's start with the slope. Slope is 55, and remember we said it's dollars over students, so $55 per student. So we need to put it in some organized manner to say, for each additional student that gets tutored there, okay, so for each 1 unit increase, for each additional student tutored, the profit increases by $55. All right, and the y-intercept, the negative 1,600 piece. So remember, for the y-intercept on the graph, it's 0, y. The y-intercept happens when the x value is 0. So let's use that for this explanation. So even if they tutor no students, so if no students are tutored, they're still in the hole, $1,600, right? So we can say Mathnasium will be in the red, so to speak, $1,600, which means they'll have no profit, they'll be owing money. So that's the way you can always interpret the y-intercept. When the x value is 0, in this case, the number of students tutored, the y-intercept is what the y value would be in the function. In part C, how much profit for 50 students in a month? And that's not as easy as just throwing 50 in and multiplying by 55, right? We got to account for the rent. So when we throw it in, make sure 55 times 50 and then subtract that $1,600 that was the flat fee that they owned to rent the building. So we should be at $1,150 to get 50 students in a month. Hopefully they're tutoring more than that, but for the sake of this problem, that's what they would earn for 50 students in a month. Part D, how many students would be needed for Mathnasium to break even, which means no loss, no gain. So they don't have any profit, but they're not negative either. So to set this one up, really what we're asking is, what would the S value be? Right? How many students would it take so that our profit at the end of the day was 0? So we don't earn anything, but we don't lose anything either. It's not like we're in the whole $1,600. How many students would it take to break even? Another way to ask that is, okay, how many students would they need to tutor to earn $1,600, right? To make up for that $1,600. Maybe that's an easier way to think about it for you. In terms of the formula, I'm going to go ahead and plug in 0 for the profit and then solve for S, solve for the number of students. So I'll plug in 0 for the profit, where P of S used to be, I'll just put a 0. And I'll solve this for S. So go ahead and add that 1,600. So 1,600 equals 55S, and then just divide by 55. We're looking at 29.09 students to break even. So right at about 29 students, just to make up what they owe each month in rent. Then after that, they start actually accumulating profit. And then the last little question here, down here in green. Graphically, what is this point? So this 29.09S, and then we plugged in 0 for the output. So the input's 29.09, the output's 0. Right? 29.09 comma 0. What is that point on the graph? Well, we plugged in 0 for the Y essentially, right? And we solved for the input, which would be like the X. So that actually should be the X-intercept, 29.09 for the number of students, and the profit at that point would be 0. So that would represent your X-intercept. All right, we talked about linear equations through a table. We talked about X-intercepts, Y-intercepts. That is all for these notes at this point. I'll see you in class.